Okay, we're in 3.2 of Barnett still, and we're going to introduce continuous compound interest, but first we're going to focus on the growth rate of a compound interest in investment. Take a look at this example. How long will it take for $5,000, RP, to grow to $15,000, RA, if the money is invested at 8.5% compounded quarterly? 8.5% is our R, right? 0.085. And what else do we have here? Compounded quarterly means that we have 4 compounding periods. Okay? How long will it take means right off the very bat that we're looking for T. That's what's unknown. So you must remember your formula for compound interest. It looks like this. And let's start plugging in what we know and what we don't know. A is 15,000. P is 5,000. We have 1 plus 0.085 over 4 raised to the 4t power. Okay, and if we go to the next slide, we actually have it right over here as the same formula. Let's start solving this problem. So now that we've substituted values in the formula, divide both sides by 5,000 so that we get 3. Okay, now 1 plus 0.085 over 4 is the same as this decimal here, and we are still raising it to the 4t power. Then what we're going to do is we're going to take the natural log on both sides. Okay, can it be the log base 10? Sure, it really makes no difference as it turns out. So let's take the natural log on both sides. We get ln of 3 equals ln of this value. But remember, you had that exponent property of logarithms, the one that's of logs, the one that said that if you have ln of, let's say, some number b here raised to the power of x, that was equivalent to x times ln of b. Remember that? That was when we learned logs, one of the properties. Well, here we have our b as 1.02125, and our power x is really this 4t. So we can bring down the 4t, make it a multiple, and multiply it by ln of 1.02125, which is just a number. Then, to solve for t, divide both sides by 4 times ln of 1.02125, and that's how you get an answer. So it's going to take about 13 years, right, roughly speaking, about 13.06 years for this investment of 5,000 to grow to 15,000 under those given conditions. Okay, well, we've talked about compound interest. Let's talk about continuous compound interest. So previously we indicated that increasing the number of compounding periods while keeping the interest rate, principal, and time constant resulted in a somewhat higher compounded amount, right? So having more compounding periods was a good thing. We got more money out of our investments. Well, what would happen to the amount if interest were compounded daily? Well, it should go up. But what if we did it the compounding every minute, or every second, or even better, every instant, every single moment of time? Well, as the number m of compounding periods per year increases without bound, as it gets bigger and bigger, the compounded amount approaches a limiting value. This value is given by the following formula, which we'll look at again in chapter 10, where we define what a limit is. But what the limit as m approaches infinity means is what happens to this expression as m gets bigger and bigger. That's all that this means, this notation. So what happens to this expression, p times 1 plus r over m raised to the mt power, right? That's just our formula for compound interest, as m gets infinitely large. Well, it turns out that this value in parentheses actually is going to give me e, and the resulting formula becomes p times e to the rt. So this whole thing really becomes p times e to the rt. Again, we don't have the knowledge yet to show you this. We have to show you this in chapter 10 when we discuss this idea of limits yet. But for now, know that it becomes p times e to the rt. So a is the compounded amount, and it's p times e to the rt. And as an example, why don't we take a look at this new continuously compounded interest? What amount will an account have after 10 years if 1,500 is invested at an annual rate of 6.75% compounded continuously? Okay, so compounded continuously tells me use the formula A equals P times e to the RT power. Okay, 10 is my T, 1,500 is my P, and 6.75, written as a decimal, is my R. Okay? Put it together into the formula. You get 1500 times e to the power of 0.0675 times 10. You get $2,946.05. It says that is only 18 cents more than the amount you receive by daily compounding, right? If instead of being continuously compounded, it was daily compounded, 365 compounding periods. Okay, but it's still more, 18 cents more. Okay, well, the last concept in this section is that of annual percentage yield. The simple interest rate that will produce the same amount as a given compound interest rate in 1 year is what we call the annual percentage yield, APY. To find the APY, we proceed as follows. The amount at simple interest APY after 1 year is the same as the amount at compound interest after 1 year by definition. So, translating this into formulas, it means P times 1 plus this APY is the same as P times 1 plus R over M raised to the power of M. Notice the T is gone because it's 1 year, so T is just 1 here. So that's why we don't bother writing it, it's just 1. Okay, so divide both sides by P, notice the P's cancel out, and you're left with 1 plus APY equals 1 plus RM, the quantity raised to the M power. Okay, subtract 1 from both sides to isolate this APY that we're looking for, and we end up with this new formula for annual percentage yield. Remember this formula. This is what we need to compute the annual percentage yield. This is also called the effective rate. So some textbooks will define it as the effective rate. Let's take a look at an example. What is the annual percentage yield for money that is invested at 6% compounded monthly? Okay, so once again, this is the formula you need. APY is equal to the quantity 1 plus R over M raised to the M power. Right, I'm getting it from the previous slide. And don't forget to subtract the 1, minus 1. Okay, so notice the R is 6%, which written as a decimal is 0.06. And it's compounded monthly, so that means M is equal to 12. There's 12 compounding periods. So to calculate APY, substitute 0.06 for R, 12 for M into the formula, and you obtain the answer. The effective rate here is 6.168. Okay, and that's the answer here. Okay, so one more example. What is the annual nominal rate compounded monthly for a CD that has an annual percentage yield of 5.9%? So I just want to point out, I just want to back up just for a sec. Notice we express this as a percentage. This should have a percentage here. So you could express the effective rate as a decimal or as a percentage, either way. So in the next problem, it's given to you as a percentage. They're telling you the APY here is 5.9%, which you can translate to 0.059 as a decimal. In fact, that's exactly what we did here in the solution. So what is the annual nominal rate compounded monthly for this CD? Start with our formula for APY. We know the APY in this problem. It's given to us to be 0.059 or 5.9%. Substitute M equal to 12 because we're told that this is compounded monthly, and solve for R. That's what we're looking for. That's the unknown in this case. Okay, well, substituting the right values and using the formula the first two steps. The third step is to add 1 to both sides, right? So that we're trying to isolate R in order to solve for it. Take the 12th root on both sides, and you obtained the following math here. 12th root of 1.059 equals 1 plus R over 12. Subtract 1, multiply by 12, and that's how you obtain the answer of R equals 0.057. So the interest rate was 5.7%. Let me show you how to enter this on your calculator. Okay, so in our calculator we're going to enter 12, parenthesis, and then what we want to do next is we want to enter the 12th root of 1.059. To do that, first you enter the index 12. That means 12th root. Go to math key is over here, and then option 5 gives you X root. That means take the root of whatever index you had entered before this operation. So if I enter 5, notice the calculator recognizes the 12th root of whatever number we put in there, and our number is 1.059. 1.059. Okay, then I press the right arrow to get rid of the square root. I do -1, and then I close the parenthesis, and that's how I obtain my answer of 0.057, which is what we had earlier.